Now that we know how to find all those lovely critical t values, it makes sense that we're going to have to use them in a formula. So this is the confidence interval for a population mean. Now remember, you don't have to memorize this formula because it goes right here in your inferential statistics info sheet that'll be given to you when you take your exams. So you have to know how to apply it and what it's referring to. So this is going to be the confidence interval for a single mean mu. So if you don't know where your average is, this is the formula for you. The critical t value is just part of that formula. See the t alpha over 2? And then the s over the square root of n should look familiar because we learned about that a little bit in section 8.1. It's essentially the standard error of the mean. There's a little bit more going on there, but roughly. Also, you need a point estimate, which is the center of your interval, which is x bar, because x bar is the middle of this interval right here. Right, now the requirements for constructing this interval are basically what we learned in section 8.1. You always need a simple random sample, and the abbreviation for that is SRS, of size little n. We don't work with non-random samples in this course. In real life, you'd have to work with non-random samples, but it gets complicated because everything becomes biased. The sample has no outliers and has to come from a population that is normally distributed or n greater than or equal to 30. So remember, all of this is to ensure that the distribution is normal. It's one of those requirements for the central limit theorem in section 8.1. Then we also need that the little n sample size is less than 5% of capital N, which is the population size. That's to ensure independence, because what happens is if you start pulling too many people or too many objects, you'll end up pulling things that are related to each other or have some kind of relationship, and then they won't be independent anymore. So you only want to pull 5% of your population size. No more than 5%, let me put it that way. Here are all the calculator instructions, but we'll kind of see those a little bit as we go. So here we have the FBI compiles data on robbery and property crimes and publishes the information. A simple random sample, there's the words again, of reported pickpocket offenses yields the losses in dollars shown below. So here are the losses reported to the FBI. And the first thing they want is a point estimate for the average loss of all pickpocket offenses. Well, they're asking about mu. The average for all pickpocket offenses in the US would be mu, population mean. Well, we don't know what the population mean is because we haven't gotten all pickpocket offenses. We only have a simple random sample. So we'll have to find x bar. And you can see that I did find it. Sorry, I lost my first couple videos. So you go to Stat, you go to Edit, you type in all your data. So 447, 313, 217, and so on. Then you go to Stat, Calculate, one variable. L1 is your list, and you do not have a frequency list because this is not a weighted mean or a mean for a grouped distribution. So you just go leave that blank and go down to Calculate and press Enter. And there it calculated it, 513.32. Lovely. All right, now we need to verify the requirements necessary to make an interval are met and show working of explanations. So first one was that it was a simple random sample. Well, we totally have that because it was given to us in the problem setup. I even highlighted it right there in yellow. All right, so we're good there. Then we need to know that the sample is either bigger than 30 would be great, or comes from a population that is normally distributed with no outliers. Well, we don't have bigger than 30. There's less than 30 in this data set. There's only 25 here. But we do, however, know that it's normally distributed with no outliers because these two graphs show us so. The one on the left is called the normal probability plot. We learned about it in section 7.4. And it shows the distribution was normal because all the dots are in those lines. The one on the right is a box plot, which we learned about in section 3.5, and it shows us that there were no outliers because there's no little star symbols here. So we've satisfied requirement number 2. We didn't have bigger than 30, but we did have the top line, which is that they're normally distributed with no outliers. Then we need to know that the little sample size, which was 25, is less than 5% of capital N. Well, we're going to kind of wave our hands like a magician at this. So we only had 25 for our sample size, and that's quite small. And capital N would be the population, or it would be all pickpocket offenses, like all of them in the whole of the US, right? In all which is a very large number, right? And since that's so large, and 25 is certainly less than 5% of that. I mean, 25 is probably less than 5% of all the pickpocketing, I don't know, in New York City alone this week, I mean, let alone all of them. Which leads me to a note. We often kind of wave our hands at the top one and the bottom one. So we often just assume that conditions number 1 and met for this course, for our purposes. We just kind of say, oh yeah. But in real life, that's not really a fair thing to do, but that's what we're going to do a lot of the time. We're just going to kind of say, well, of course we have this. Of course we have this. But in real life, you don't actually always have random, and you don't always have less than 5% of your population. We tend to focus more in this course on number 2. Not that the other ones are not valid, but they're a little bit harder for us to check, whereas the middle one is pretty easy for us to check. All right, so now let's construct that confidence interval. We're going to have to show the formula, the substitution, all that stuff. Okay, well, it's going to take some work here. So we start with the formula. The formula is pretty straightforward. We know that the formula, and actually I'm going to make a table here because I think I'm going to have to do some work on the side over there. So we know the formula is x bar plus or minus t alpha over 2 times s over the square root of n. So you just write the formula, you've already got a point. The real work comes with the substitution. So we need to substitute. We need to find some values. And I have them found for us. So 513.32, that should be pretty obvious. Now, where did the 262.23 come from? Well, it's funny you should ask. 262.23 is right here. See, it's SX. And while I'm on the subject, N is right there. So X bar, S, and N all come out of one variable stats. So let me make that note over here. 1 second. All right, so those all came from one variable stat in the calculator. So then the question becomes is, where does the 2.064 come from? Well, all right, so our sea level was 95%. That means that our alpha is 0.05. All right, great. That means that alpha over 2, however, which is what we really need. When you look at the formula, let me go back. It actually, oh, why am I going back there? Silly. It's right here. Alpha over 2. It says very explicitly what you need. So you need alpha over 2, and alpha over 2 is 0.025. Okay. Degrees of freedom is n minus 1, which would be 24. Okay. All right, so let's do inverse norm, or inverse t, excuse me, because this is a t value. 0.025 comma 24. And that gets me distributions, inverse t, 0.025, and 24. Paste. Enter. There's 2.064, negative. Now, if you really like the tables better, and I actually do for quick reference, it's really quick. So you just go to the 0.025 column, go down to 24 for your degrees of freedom. There it is, 2.064 right there. So let me put that in. So this is 2.064 negative. It doesn't really matter that it came out negative. All that matters is t-table. All that matters is that you have the value, because the formula itself has a plus or minus in it. So it doesn't matter if you did negative, that's just the negative one. Positive would be the positive one. It's all good. All right, so finally we need our result. Now for getting this, what we're going to do is we're going to go to the calculator. So let's see here. If I go to stat, I go to tests. If you remember on the inferential statistics sheet, right here in gray, I tell you what to use, which is t-interval. So you need to look through your list. It should be number 8. You want t-interval. All right, now at this point you have an option, and these options are going to keep showing up, so we want to go through them real carefully. You have data as an option or stats. Now data you use if you actually had a column of data that you entered. So if you went to stat edit and you put in data for this problem, which we did, you would use data. So if I use stat test number 8, I pick data, but I tell it L1, so second 1 because that's where my data is. Frequency we always leave as 1. That's a more advanced topic than we cover. And then C level is your confidence level, which is 0.95, and you go down to calculate. You don't need to press enter again, it'll actually run it. And there it is, 405.08, 621.56. Simple as that. And you'll notice that running this t-interval also gave the x-bar, the s, and the n. You actually could have done this from the start. You didn't actually have to do the one variable stat because the interval itself will give it to you. Now let me just show you how to use the stats one just in case. So if I go to stat, tests, I pick number 8 again, which is t-interval. Let me pick statistics. And so then what you would do is you would type in 513.32, 262.23, say. 25 was my sample size. 0.95 was my confidence level. And I go to calculate. And there we have it. Right? And this one actually didn't matter whether we did data or stats. Usually data is more accurate, but this one worked out the same both ways, which is great. So now you know how to use your calculator to do the confidence intervals, which are the instructions right here in these two. Right? One of them uses data, that's the top one, and one of them uses stats, which is the bottom one, the bottom set of instructions. Now, as for how to interpret that interval, well, it works just like it did before. We are 95% confident that the true average amount of all pickpocket offenses in the U.S., I should say in the U.S., in the United States, which is mu, is somewhere between $405.08 and $621.56. As with most math things, you always have to include units if they're available, which they are in this case. All right. Then let's see, a law enforcement official states that the amount of money for pickpocketing offenses in his area is lower than the national average, with an average of 420. So I like this word's lower than. Let's look at those. I'm going to highlight those. And then it has an average of 420. That's nice. If this amount is correct, does the local appear, oh, that's a typo. Does the local local area, sorry, it is not a typo. Local area appear to be different from the nation. So he's saying, or she's saying, look, we're different in this area because we're lower than the national average. We're only at 420. Well, that's lower than 513. That's true, but that's not lower than the interval we'd make. So this is not true, right? Our claim that claim is not correct according to the interval that we've made. So the claim they're making is that 420 is smaller than the national average, which is the interval. That's what the interval is for. You're talking about the national average for mu. Okay. Well, that's not supported by our interval. Right? Our interval does not support that because lower than the average would mean that 420 is lower than our interval. But 420 is within our interval. It's inside it, right? The 420, if they had claimed that it was the same as the national average, then we would have supported their claim. Or if their average had been 320, then we would have supported that, right? But saying that it's lower than the average when 420 is right smack dab in the middle of your interval, no, that doesn't support it. They're claiming that it's lower than, and 420 is not lower than these numbers. 420 is in between these numbers. If they had claimed that his local area was the same as the national average, then we would have supported that claim. All right, so I just added another one. So if he had claimed that 420, right, his local area, which was 420, was the same as the national average, I'm right on with them, right? I'd support that. If their local area average had been 320, then we would have supported that it was lower, right? Lower. But having 420 does not support lower because 420 is right in there. And we're done with that question. And I'll stop right there and I'll pick up at the next example in the next video.